Okay, you've been asked to calculate the probability of making free throws. We have a 60% free throw shooter, and we want to figure out the probability that the person, of what the probability the person will make. All right, Kyle, what are our options here? What are the possibilities of how many that person could make?
Well, you can make one.
Could make one? Two? Three? Is that it? Or you not make any. Right. That's all the different possibilities we've got going here. Is this an example of a discrete or a continuous distribution? It is discrete, and the reason why is because there's a countable number of outcomes. There's only 4 things that can happen here. A person can make anywhere from 0 to 3 distributions. All right, what'd you do? How'd you fill out this chart?
I made a tree.
Yeah, it's a great choice here. Okay, I think making a tree is a really good way to go here. And why was the tree a good way to go?
Because it allows you to
see all the different ways something can happen. That was kind of the tricky part of this particular problem. All right, so we want to find out the probability the person doesn't make any. How would you do that for this tree?
You would multiply 0.4 3 times.
Yeah, and is that the only way down the tree to miss all 3? Yeah, there's only one way this can possibly happen. Okay, 0.4 times 0.4 times 0.4. Is it okay if I write a 0.4 to the third? Is that okay? Does that make sense? Okay. What'd you get for that?
I got 0.064.
Okay, that makes sense. Person makes 60% of their free throws. It's possible they could miss them all. In fact, the probability of that happening is about 6.4%. Not very likely. All right, but now things get interesting as we get to making one free throw. Now, did you do it wrong first? I guess one way you could do this, probably just making one, you might have done like 0.6 times 0.4 times 0.4. Did you do that first? Did you try that first before you did the tree? I'm seeing some nods. Some of you maybe did that. And I gave this as your hint. So if you went through with that way, I think you found out, wait a minute, these don't add up to 1. I must be missing something. How many ways down the tree in this particular problem can we do to make 1 and miss 2?
You can make 1 and then miss 2 right after that.
So there's one way here, okay?
Or you can miss 1 and then make 1 and then miss 1.
Okay, there's that way.
And then you can miss 2 and then make 1.
That's right. There's 3 different ways down the tree. And notice what I did here. See if that's okay. I wrote that as making, miss, miss. So is that okay to write it like that? 0.6 to the first, 0.4 squared. Is that all right? And then this one was 0.4, 0.6, 0.4. So I wrote it the same way. Is that okay? 0.6 to the first, 0.4 squared. There's 2 of them there. All right, kind of got a cool little formula for you on how to figure out how many ways down the tree you'd have in any situation. Let's say we're shooting 20 free throws, and I want to find the chances of making 8. First of all, I don't want to draw that tree, and I definitely don't want to try to find all the ways down the tree. Is there an easier way? And in fact, there is. And this is the formula that does it. You've actually used this formula before, maybe way back in Algebra 2. This is said as n choose k. It's also the combination. You might know it by combination. Another way you might see this is nc, I'll use k. What this is saying, okay, just put it down. Remember this? Remember that you had, like you did problems like there are 10 people and I have to choose a committee of 3. How many different committees can I make? Is that ringing a bell back from Algebra 2 when you guys did probability? Okay. Here's the fancy formula to this thing. It is n factorial over k factorial n minus k factorial. Okay. So for this particular problem, I have got 3 shots and I want to make 1. Now you're not going to have to remember all this stuff. I'm just going to show you how it works. So this, by the formula, would be 3 factorial over 1 factorial, and the bottom 2 always add up to each other, 2 factorial. So for this particular problem, it would be 3 times 2 times 1 over 2 times 1. Those cancel, and we came out 3. Okay? So this formula will tell you how many different ways down the tree you can do something. Right. Fortunately, we have this button on our calculator. right, so if you want to do 3, choose 1, you first would need to put the 3 in. And then the button can be found in math. So if you go to math, over to probability, that's how I get you guys on the board, and then NCR. And then I hit the number 1. It puts that formula into your calculator, and hopefully when I hit this, it'll be 3. How many ways down the tree was it to make 2 free throws? It was 3 as well, wasn't it? Wasn't there 3 ways down the tree for that? Well, let's see if that works. 3, choose 2. I hope this comes out 3 as well, and it does. So go answer my question. Let's say we shoot 20 free throws, and I want to find out how many ways down the tree to make 8. How many ways down the tree would it be? 20, choose 8. Wow, anybody want to draw that tree? Start counting. Okay, so a lot of ways down the tree on that particular problem. Okay, so can tell us, that's how we can figure out, it's a mathematical formula to figure out how many different ways down the tree we can go. All right, so when you got these 3, back to you, Kyle, when you got these 3, what did you do with these 3 numbers? Added them up. That's our multiplication rule and our addition rule. So help me out here, what was the probability of making exactly 1 free throw?
It was 0.288.
And then making 2 free throws?
That was
0.4 something? 432. And a couple of ways you could find the last one, right? You could add those up and subtract from 1, or there's only one way down the tree where you make all 3. That must be 0.6, 0.6, 0.6, which turned out to be
0.06.
206. And if you check those, they do in fact add up to 1. Kind of makes sense. Let's think about this. I'm a 30% free throw shooter. What would have the highest probability? Yeah, making 2 out of 3. That kind of makes sense, right? That would seem like it would happen the most likely. The least likely, since I'm a pretty good free throw shooter, I shoot 60%. The least likely was that I would miss them all. All right, making your graph. You know, like again, it's a style thing for me, but I like keeping these discrete probability distributions separate. If you didn't, it's not necessarily wrong. You have your probabilities here. First one only goes up to 6%. Second one goes up to 28%. Third one goes up to 43%. Chances of making the third one is 0. All right, Kyle, now let's answer these questions over here. I want to know the probability that I make exactly 0. What would that be from our chart?
0.064.
Yeah, that was right on the chart, 6.4%. Now we got to be a little bit careful. What's the probability of making less than 2? How would you do that? It would be...
That would be 1 and 0 added together.
Yeah, so we'd add these 2 together, the 6 and the 28%. What does that come out to? About 0.03... Sorry. 35.2%. How about the next one? Probability of less than or equal to 1.
That'd be 1 and 0 added.
It'd be the same exact thing. So everybody notice that these 2 are actually saying the exact same thing. The less than and less than or equal to symbols are very different when you're dealing with the discrete probability model. So this actually would be the same exact answer. And then finally the last one, greater than or equal to 2. Another way I can say the last one is at least 2.
Which would be those 2 added up, which is
Those last 2 added up and you get?
0.638.
Okay. Did you come out? Okay. All right. Well, there's got to be an easier way than to make a tree diagram for every single problem that you want to do at this particular type, and there is. All right. This particular type of problem has a special name, and it's called the binomial distribution. In order to do a problem of this type, okay, if it meets 4 criterias, it's known as a binomial distribution, and we're going to have a little shortcut formula to show you in just a second. Now, we've done many distributions in here already. We've done the normal distribution. We've talked about that. We've had the uniform distribution. Those are both continuous distributions. Okay, this is a discrete chart, and it's referred to as the binomial distribution. So let's see, you're going to have some problems tonight, and they're just going to ask you, tell me, is it a binomial distribution or not? Okay, it means to meet all four of these. It's the big four. Tomorrow I'm going to come in class, I'm going to have my hand like this, and I'm going to say, is that a binomial distribution? And you're going to read off all four things to me and tell me that it is. If it breaks any of these, it's not a binomial distribution. All right, Kyle, we'll stay with you. It needs to have a fixed number of trials. In this particular problem, is there a fixed number of trials, and what would that be?
Yeah.
Yeah, it only took 3 shots. Okay. If you were doing the kind of problem which would be, hey, I'm going to keep shooting until I miss. Okay, well, I might shoot 10, I might shoot 20. If I'm Aaron, I might shoot 1. Sorry. So it's not a fixed number of trials. Okay, so it could keep going, so it's different. So that wouldn't be a binomial distribution. In order to be a binomial, it has to be a fixed number of trials. I got Goldman earlier, so no. Only 2 options, success or failure, in this particular problem. Now, by meaning 2, okay, so it's kind of in the title there. In this particular problem, are there only 2 options? And what are they? You're going to make the shot or you're going to miss the shot. Okay, so 2 for 2. All right, the next one. All the observations must be independent of each other. And I've told you what that means here. Remember, this is how we say it. So in other words, knowing what happens before, does it affect the next one? How about this one? Do you think these are independent?
Yes.
Why?
Because no matter how many times you shoot it, it'll be 0.6%.
Yeah, you're kind of skipping ahead. These are very much related. I don't necessarily see how they're so different. But in terms of independent, it would be something like this. Knowing that I made the previous shot does not affect the chances that I make the next shot. Now this one, I don't know. I mean, talk about myself. If I missed the first free throw, I was in mortal fear. I was lucky if I hit the rim on the second, so I was so scared I was going to miss them both. So I don't know if it follows like that, but in order to do the binomial distribution problem, we have to assume that they are independent. And like I said, the last one kind of follows, and that's what you just said. The probability must stay the same on each single observation that you do. So shooting the free throws, it has to stay 0.6, and that's what it did down the tree. Obviously, dealing cards without replacement, if I get a red one, then the probability changes for the next red one. So that wouldn't be a binomial distribution because the probability changes. So if these 4 conditions are met, we can either draw this tree, but there's a nice shortcut formula that will get us there. And this formula should make sense to you. Go find it on your green sheets. I believe it's on page 4. It's on your probability page. Again, this is not one that you'd have to memorize, but it's one that you will memorize. You're going to be using this so many times. All right, let's take a look at this formula and see if it kind of makes sense to you now, given the problem that you just did. Let's focus on making one of the 3. Okay. Now remember, I said that making one of the 3 means that you're going to have 1.6 that you're multiplying and 2.4s. Okay, and we ended up doing that same thing 3 times. Let's take a look at this formula. Does this do this for us? Now remember what this means. This is how many times down the tree. P is the probability for success. So in this problem, making a free throw, that would be 0.6. How many makes do I want? 1. This is the probability for failure. So the probability of success is 0.6 and the probability of failure is 0.4. How many failures do I want? In this problem, I wanted 2, which is your 3 minus 1. Okay. So for this particular problem, you would just write 3, choose 1. The probability for success is 0.6, which is you want 1 of those, and the probability for failure, and you want 2 of those. And you don't have to write the 3 minus 2 if you don't want to. Just remember, I'm shooting 3 shots. I want 1 to go in, and I want 2 not to go in. Well, let's see if that formula works. It should. Let's plug it into our... So, 3, choose 1, and you know what? I better put parentheses around it. 3, choose 1, and then 0.6, and I want to make 1, and I need to miss 2. Oops. I gotta go up arrow, sorry. Try it again. 3, choose 1, and then 0.6, up arrow, 1, raised to the first power, times 0.4, up arrow, raised to the second power. Third time. 3. Choose 1. Parentheses, 0.6, up arrow, 1. Parentheses, 0.4, up arrow, 2. Get the right answer finally? Okay, so for the first 10 years, your founding fathers learned about the binomial formula. That's how they had to do it. And then I think a few years ago, one of them showed me this button. So you can use this button too. And it's a very cool button. And it's the Binomial Pdf button. And what this button does is it plugs that in for you to your calculator. Now, Binomial Pdf means probability distribution model. So it's going to give you these numbers. That's what the whole point of the Binomial Pdf button is. So it's a Binomial Pdf. Then we put in how many free throws we're going to shoot, what's the chances of making a free throw, and how many do I want to make. You can find that in distribution. So it's second vars. Second vars is distribution. Cruise down to the Binomial Pdf. There it is. Hit enter. And then let's hit our 3 parameters. I'm going to shoot 3 free throws. I'm a 0.6 shooter, and I want to make 1. Blammo. You like that button? Yeah.
What's a PC?
Well, we'll get there in a second. Okay, now here's the key. What I want to see when you're doing these problems on your homework or your test, I want to see the formula. I want you to show me how you're going to use that formula and plug it in. And then I don't care what you do. You can use that button or not use that button. Come up with that answer and then write your sentence. What I don't want to ever see on your paper, ever, is Binomial Pdf. I don't want you to give me calculator talk. Ever. Okay, your reader's not going to know PDF, doesn't care. However you get it, it's your business. But you need to show me the formula, plug in your numbers, and go get your answer. So then last year, one of your founding fathers showed me this. I thought it was the coolest thing in the world. We can actually create that probability distribution function all at one time. All right, the left-hand side, all the different outcomes we have to come up with. So that's 0, 1, 2, and 3. But now if you highlight the top, and let's just do our PDF function. So go into distribution, Binomial Pdf. So I'm going to take 3 shots. I'm a 60% shooter. And then what would the third parameter? What would we want to put in here?
L1.
L1, yeah, because I want it to go down and for the different make situations. So put in L1, close off your parenthesis. Bam! That's really cool. None of your founding fathers used that one. Except last year. Okay? All right, so I want you to try a problem on your own here. See if you can do it. Much like you guys, when you come in and take your tests, you have no idea how to do the multiple choice. In fact, you're guessing on all of them. So you've got 10 problems, and you're guessing on all of them. What do you guys have, A through E? That's usually what you have, A through E. So you're guessing on all of them. You have 10 problems. I want you to calculate for me the probability that you'll get exactly 6 of them right. I want you to go through the whole process. What do I need to see as if this was the problem? 10 multiple choice questions. You're guessing completely on all of them. And I want to know the probability that you will get exactly 6 out of those 10 correct. What?
How many options do you have for the answer?
A through E. That's what you have on your test, A through E. So you want to go through the checks to make sure you know it's binomial. Then I want you to solve it if you can. Paper now. I should see exactly what I want to see come test time. Alright, Dalton, let's go through the steps. Let's first of all check out to make sure this is in fact a binomial distribution. Do we have a fixed number of trials?
Yes.
And how many in this problem?
10.
Yeah, there's 10 questions. I didn't say you might have 11 or 10 or might change. It's going to have 10. It's always going to be 10 for this problem, so we have a fixed number of trials. Do we have only 2 options for this?
Yeah.
What are they?
Right or wrong.
Right or wrong. Kind of a trick question, right? You had 5 options for the test, but the question we're asking is how many right or wrong that you get. So in actuality, there really are only 2 options. You're going to get the problem right or you're going to get it wrong. Are each of the questions independent of each other? Yeah, well, if you got the previous one right or wrong, it doesn't change the probability of the next one. It's still going to go right back. And what is the probability for success on each one of them?
0.2.
And that's correct. You had 5 options, only one of them's right, so you got a 20% chance for each one of them. So solving this problem, Dalton, what's the first thing you would do?
Write the formula.
Very good. Okay, write the formula down that you're going to use.
So P x equals 6 equals.
What? What am I doing first?
Oh, sorry. Equals N choose K.
And choose K. Very good.
P K.
Uh-huh.
And 1 minus P N minus K.
Very good. All right, now we can plug it in. So I'm trying to figure out the probability of getting exactly 6 of them correct. So that would be?
10 choose 6.
Uh-huh.
Times 0.2 to the first. Times
Okay, say again.
0.2 to. Oh, 6.
Yeah, I need 6 of them right. I know it was in the last problem, it was just the first. But if I'm going down my tree, to get 6 of them right, I got to be 0.2, 0.2, 0.2, 0.2, right? There's going to be 6 of them, and there's going to be 4 mistakes as well. And that's where the 0.8s are going to come in, and there's going to be 4 0.8s. Okay, so the probability of success is 0.2. How many successes do I want?
6.
And the probability of failure is 0.8. And how many failures do I want?
4.
You can put 4, or you can put the 10 minus 6 there. That's fine. Now again, at this point, you can plug in if you want. I don't even recommend you mess with it. Just go straight to your PDF and plug in those parameters. And I think you get is it 0.0055, something like that? 0.5% chance. You got 0.5% chance of getting a D. Which I've seen many times since you're on your tests. Alright, I want to show you another button that's pretty cool too. It's called the Binomial Cdf button. The Cdf button is kind of like a ogive button. Don't nod. You don't remember ogive. No, you do. Remember percentile button, right? It's the percentage at or below. And then we drew an ogive that went up in there, and you drew. It's a percentile finder. May 10th. May 10th. So what it'll do, this CDF button, is it will add up. It'll basically do this problem for you. Remember here, someone said, hey, we need to add up 0 and 1. This is both the same problem. That's what the CDF button will do. It'll start adding up at the probability of getting 0, and it'll go as far as you want. So the way the CDF button works is it wants to know how many shots you're taking, 3. What's the probability of success, 0.6, and then how far do you want me to add to? So if I was doing problem number 2 and I was using the CDF button, so you go back into distribution, and right below PDF is CDF. And so it'd be 3, comma, 0.6, comma, 1, and that will add up the 0 and the 1 place. And there we got our 35.2%. Okay? All right, so let me continue on with the problem that we're doing. 10 multiple choice questions. Okay, now I want to know the probability that you get at least 6 correct. At least 6 correct. You're going to have to write down the formula. I need you to plug them in for 2. Remember we did 3 before, but the formula's kind of long, so you got to figure out how you're going to plug in for at least 2. But I want you to find for me the probability of getting at least 6 correct. Go to work. Down the road you can use that CDF button if you can figure out how to use it. But you are asked to find, you're guessing on every single problem. What are the chances you get a D or better on this test? 6 or better. How would you show your work for this problem? let's work together a little bit here. All right, Jason, what does at least 6 mean? What would that mean to you if you got at least 6 of the problems right? That means you got
6 or more.
6 or more. Okay, so you get 6 or 7 or 8 or 9 or 10. Now, none of you did this, but this is one way to do this as well. I mean, to get it right and the probability of getting it right. So what are all the different possibilities that could happen? Like most of you get none of them right. Okay, all the way to 10. This is not something you have to do, but I want you to think in terms of this. So how about the probability of at least 6? Don't I want to add these guys up? Isn't that the goal here, is to add all those up? That's the probability of at least 6. So I guess you could do the PDF for each one of those and just add them up. Does everyone remember this thing? Isn't that something we just learned? And so then theoretically, couldn't you do 1 minus this? And wouldn't it leave me with what I'm wanting here? Okay. So that's the way to do it. All right, our challenge is how do you want to represent this showing your work? So what I want you to do is give me the original formula. And I saw a lot of you doing different things out there. One way I looked at that and I liked was probably that x is greater than or equal to 6. And then you did something like that's the probability of 6 plus to the probability of 10. I like that. What's another thing you could have done? You could have done 1 minus the probability of 0 to the probability of 5. Does that make sense, both of those? So in terms of showing your work, you could have done either one of them to show your work. You could have done this one. So show me the probability of 6. That's 10 choose 6. 0.2 to the 6th. 0.8 to the 4th. Plus, dot, dot, dot. Show me the last one. That would have been okay. You could have done it this way, where 1 minus and plugged in the probability of 0 and probability of getting 5. That's fine too. But what's kind of a cool way to enter it into your calculator? That would be nice and quick. Now I don't want to see this on your paper, but how could I have done my calculator in a real quick way to get this done? Okay.
You could use the Binomial Cdf to
Okay, so what would you type into your calculator? Would that give me the answer to greater than or equal to 6? Do I need to draw that picture again?
No, then you'd have to subtract that.
Right, so if you just entered that into your calculator, would that leave me with the 6 through the 10? Okay. Now remember, I don't want to see this. Don't show me this. But you plug that into your calculator and that'll add up to 6 through the 10. Anybody get an answer for that? Still pretty low probability, right? 0.11? No? $10, comma 0.2, comma 5. So only a 0.6% chance that you're going to pass this test if you're guessing on all the multiple choice. Okay? All right, throwing a lot at you, but I can promise you that this formula does make sense. If you were able to get that tree diagram, you're just writing the tree diagram in a more condensed form. Learn about the binomial distribution. In order for you to have a binomial distribution, 4 things must all be true. Fixed number of trials can only have 2 possible outcomes. They have to be independent. The probability can't change. If that's all true, you would create a tree like this. This is the formula that gets it. This part tells me how many ways down the tree. This is the probability of success times to the number of successes. Probability of failure to the number of failures. Learned a couple of shortcuts. Don't want to see these on your paper. Okay, but feel free to use them to shortcut to your answers. Okay, any questions, comments?